This video is a summary of all the topics covered in the third topic of the specification of AQA GCSE Chemistry. Now, a lot of these are topics where really you need to practice and learn a method for a particular calculation rather than just revising with flashcards, but hopefully this summary is enough to refresh your memory before an end of topic test or your GCSE Chemistry Paper 1. The quantitative chemistry topic does have quite a few bits that are only for those taking higher tier or only for those taking triple science, so watch out for the headings at the top of the screen to see whether you personally need to know something or not. There are a number of scientific laws called the law of conservation of something: momentum, energy, also mass. So the word conservation means keeping things the same. And so the law of conservation of mass tells us that in a chemical reaction, no atoms can be lost and also no atoms can be made. Now this is important because it means that when we write a chemical symbol equation, it needs to balance. In other words, there need to be the exact same number of atoms of each type on the left-hand side of the equation as on the right-hand side. So this equation here is one you're probably very familiar with. It's the equation for photosynthesis, and if we were going to add up all of the atoms on either side, we'd find that both sides of the reaction have got 6 carbon atoms, both sides have got 12 hydrogen atoms, and both sides have got 18 oxygen atoms. So we would describe that symbol equation as being balanced. We're just going to look briefly at some chemical symbol formulae because it's impossible for you to balance equations if you don't understand what they're trying to tell you. Now, when you're balancing an equation, the only thing that you're allowed to change is big numbers at the front, what we call coefficients or multipliers. So this 4 that I've written here applies to everything that comes after it. And while I can change that number 4 to a different number, I can't alter these small numbers that are in part of my chemical symbol formula, because those small numbers tell me things about how this substance is bonded, and it's determined by the precise atoms that are in that compound. So I can't edit any of them. Now that 4 at the front, what we call a coefficient or a multiplier, it applies to everything that comes afterwards. But what does come afterwards? Well, the first bit is quite easy. Inside my brackets, as it were, I've got 2 atoms of aluminium. And then I've got some actual brackets which are part of the formula, and you can see there's a 3 after them. So the 3 applies to everything that's in that bracket. It doesn't apply to the aluminium because the aluminium is not in the bracket. So inside that bracket, I've got 1 sulfur atom and I've got 4 oxygen atoms. And then the 3 applies to all of that bracket. So that means that I've got 3 lots of 1 and 3 lots of 4. So I've got 3 sulfurs and 12 oxygen. And then, as we said, this coefficient at the front applies to everything. So I've got 4 of everything that's come afterwards. So in total, that would give me 8 aluminium, 12 sulfur and 48 oxygen. If you're going to balance a symbol equation, the first thing you need to do is to count up the number of atoms on each side of the equation. So here I've got 1 atom of iron on the left and 2 on the right, and 2 atoms of oxygen on the left and 3 on the right. Next, I need to pick one of my elements that only appears once on each side of the equation. Now here that's all of them, but in a more complicated question, often oxygen in particular pops up multiple times, and you definitely don't want to start there. So I'm going to start with oxygen here, and what I'm going to think about is what is the lowest common multiple of the numbers of atoms I currently have. So I've got 2 and 3, what is the lowest common multiple of 2 and 3? What's the smallest number that they both go into? And that would be 6. And next I'm going to think, what do I need to multiply 2 and 3 by to turn them into 6? So 3 I would multiply by 2, and 2 I would multiply by 3. Now those numbers are going to become my coefficients. So here I'm thinking about oxygen, so they're going to go in front of the chemicals that contain oxygen. So this 2 here goes up here, and this 3 here is going to go in front of my oxygen. Now I need to recount my atoms because they're going to change things. So remember that 2 is applying to everything that comes afterwards. So we've got 6 oxygen, but we've also now got 4 iron. And then on the left-hand side, we've got 6 oxygen. So oxygen is fixed, that is balanced, and now I can pay attention to my iron instead. And so my lowest common multiple of 4 and 1 is just 4. So 4 we can just multiply by 1, and obviously we don't have to do anything with the number 1, but if it was a number that wasn't 1, I would then multiply those together. So you can see at the top there I've just put a little times 1, just so you know what to do with that if it is a number other than 1. And then 1 we would multiply by 4, and so that number there is going to go in front of my iron. And if I count up everything, we're now fully balanced. As well as meaning that symbol equations must balance, the law of conservation of mass also means that if I know the mass of the products, I also know the mass of the reactants because they'll be the same as each other. And if you think about it, this makes sense. If we've got the exact same atoms, they've just been swapped around into a different order, they're still going to have the same mass. So a very straightforward question, probably on the foundation tier paper, might ask us to work out the mass of a chemical that's not included in our data. So here I've got 85.8 grams of propane reacting with 312 grams of oxygen, and it's producing 257.4 grams of carbon dioxide and some water, and I don't know how heavy the water is. So if I add up the mass of the reactants, I get 397.8 grams, and therefore the mass of the products must also be 397.8 grams. So if I subtract the mass of the carbon dioxide, then I get the mass of my water, which is 140.4 grams. Now this can start to get a little bit more complicated when we start looking at reactions that involve gases, where the mass may appear to change. Here's an example. Say I take a 6 gram strip of magnesium ribbon and I put it on some scales. I know that the mass is 6 grams. I then heat it up and let it react with some oxygen, and then when I measure the mass again, I have 10 grams of magnesium oxide. Now it might look as if that reaction has gained mass, and we've just said that can't happen. But what's actually happened is that 4 grams of oxygen that was previously floating around in the atmosphere and wasn't actually pushing down on that balance is now bonded to the magnesium, and so its mass is being accounted for by the balance. It's not that we've got any new atoms, it's just that they're actually interacting with the balance. And so this is what you'll see when you have a reactant as a gas. The reaction will appear to gain mass. This also happens in the opposite direction where a gas is a product. It will appear to lose mass. So say if I take 5 grams of calcium carbonate and I heat it up to a very high temperature so that it thermally decomposes, it will break down to make 2.8 grams of calcium oxide, which is what I'm left with and can weigh, and then 2.2 grams of carbon dioxide. And that carbon dioxide is a gas and it escapes and is released into the atmosphere. So it's no longer pushing down on my balance. So even though the total mass of products is the same, it appears as though my reaction is losing mass. Next, you need to be able to calculate the relative formula mass, also known as MR, of either a compound or a molecule. This is done by adding together the relative atomic masses of all of the elements in that substance, in the proportions that they are in the substance. So for instance, if we're looking at sodium oxide, I can see from the formula here that 1 mole of sodium oxide contains 2 moles of sodium atoms and 1 mole of oxygen atoms. So therefore I'm going to add together 2 lots of 23 because that's the mass of sodium and 1 lot of 16 because that's the mass of oxygen. So I get a total of 62 grams per mole. In other words, 1 mole of sodium oxide has a mass of 62 grams. We can use the relative formula mass to calculate the percentage by mass of a particular element in a compound. So let's say we were asked to calculate the percentage by mass of sodium in sodium oxide. In other words, what percentage of that compound is just sodium? I'd start out by calculating the mass of sodium in sodium oxide. So not just 23, which is the mass of sodium, but 23 times 2, because there are 2 atoms per formula unit. Then I would divide that by the total mass of sodium oxide, which I worked out in the previous slide. And then I would multiply that by 100 to turn it into a percentage. So the calculation I'd end up doing would be 46 divided by 62 times 100, which would give me an answer of 74%. Whenever you make some kind of physical measurement, whether that's measuring temperature or time or a length, there's going to be some uncertainty, which we can define as the spread of values about the mean. And this is going to happen because no measuring instrument is 100% accurate, but also because of random errors. So a random error is one that is happening because of natural fluctuation in the true value, whereas a systematic error is one that's happening because your equipment is poorly calibrated. Say a balance that always reads 5 grams too heavy, or a thermometer that always reads the temperature 1 degree too low. Now, in order to overcome systematic errors, we would need to calibrate our equipment more carefully. But in order to overcome random errors, we tend to take many repeat readings and calculate a mean. But sometimes we still want to express that there is some random error there. So this can be expressed as either precision or absolute uncertainty, or as percentage uncertainty. Before I can do any calculations with my data, I need to look at all of them and look at the general pattern and see, are there any pieces of data that are so far removed from that pattern that I don't think that they're legitimate, I don't think that they're valid. So I would remove these and I would say that these are anomalies. And very, very often AQA will ask you to calculate a mean and tell you to disregard the anomalous result or the anomaly. And so this is the one that's very different that you want to remove. So when I'm reporting on a particular value, I can first of all remove any anomalies, and then calculate a mean by adding up all of the pieces of data that are left and dividing by the number of pieces of data there are, which in this instance gives me an answer of 27.7. And then when I'm talking about the uncertainty, I can think about the distance from that mean, or also half the range. So here my range is from 31.2 down to 24.2, which is 7, so half that range would be 3.5. So I would report my value as 27.7 plus or minus 3.5. Now I've just been talking about a mole of sodium oxide and a mole of sodium atoms, and actually if you're taking foundation tier that's not going to come up in your exam, but it's quite simple to understand really. The mass of a single atom is far, far too small for us to measure directly, so we don't measure the mass of a single atom. Instead we measure atoms in multipacks, and we call that multipack the mole. So when we say that the relative atomic mass of sodium is 23, what we mean is that 1 mole of sodium weighs 23 grams. And that's compared to a gold standard, which is the carbon-12 isotope. Now this mole is just a big number. In the same way that you understand that the word million means a 1 with 6 zeros after it, or dozen means 12, a mole just refers to a number, and that number is 6.02 times 10 to the 23. And this is sometimes referred to as Avogadro's constant or Avogadro's number. So since mole is such a big number, it's possible to have half a mole and decimals of a mole. So in the same way that you can have half a million, you can have half a mole. So if 1 mole contains 6.02 times 10 to the 23 atoms or molecules or ions or whatever it is that you're trying to count, then I can therefore say that half a mole of those atoms or whatever contains half that many particles, so 3.01 times 10 to the 23, and 2 moles contains double that number of particles. It's important to understand here that the identity of a substance you're looking at isn't going to affect the number of particles in a mole. So although 1 mole of carbon has a different mass to 1 mole of oxygen, they both contain 6.02 times 10 to the 23 atoms. Very often in your calculations in GCSE Chemistry, you're going to be given a mass of a particular substance and you're going to need to work out how many moles there are. And there's a calculation that we can use for this. My classes tend to refer to this as the mass is Mr. Mole equation, and the MR really stands for relative formula mass, but you can use the exact same process if you're thinking about something that has a relative atomic mass instead. Basically what we're saying is that the mass can be found by multiplying together the relative formula mass by the number of moles, and we can rearrange this to allow us to work out what the number of moles is. So if I rearrange my equation, I get mole is mass divided by MR. Actually, strictly speaking here, this is AR because it's an atom rather than a molecule or a compound. But at any rate, we can do 483 divided by 23 to give us 21 moles. We can start to put together our knowledge of moles and their masses together with balanced symbol equations to do more complicated calculations called theoretical yield or predicted yield, or sometimes reacting masses. So yield is the word we give for the amount of product that's made in a reaction, and theoretical yield is the maximum amount of product that you could make. Some people can find these theoretical yield calculations very overwhelming, so I find it helpful to start from the point of view of a non-chemistry situation. So imagine that you've gone to the supermarket and you're buying apples to make some apple pie, and the price for the apples is £3 per dozen, and you've got £12 to spend. And then we want to figure out how much apple pie can we make based on that. The first thing you'd do is work out how many apples you can buy for that money. So this is our mass is Mr. Mole equation. We would figure out, based on the mass we've got, what's the mass of a single mole, and therefore how many moles do we have. Then you'd want to work out how much pie you can make using these apples. So this is where our balanced symbol equations come in. In my story, I'm told that half a dozen apples will make 1 pie. And I've got 4 dozen apples, so therefore I can make 8 pies. So let's look at this in terms of actual chemistry. If I've got 510 grams of aluminium oxide, how much aluminium can I make? My first step is to figure out how many moles of aluminium oxide do I have. I'm going to use my mass is Mr. Mole equation, but to use that I need the Mr, the relative formula mass. So I'm going to calculate that the relative formula mass of aluminium oxide is 102 grams per mole. I can then put that together with the fact that I was told that I had 510 grams. So 510 divided by 102 tells me I actually have 5 moles. Now I'm going to need my symbol equation. So think of the symbol equation like a recipe. I put this many of something in and I get this many out. So I can see here that for every 1 aluminium oxide, I'm going to produce 2 aluminium. So that means that instead of the 5 aluminium oxide that I started with, I'm going to finish with 10 moles of aluminium. And then I'm going to use mass is Mr. Mole again, but this time with the relative mass of aluminium. So 10 multiplied by 27 gives me 270 grams, which is my final answer. If you're taking the triple science exams, then you need to know that percentage yield is a measure of how successful your reaction has been. So we compare the mass of the product that you did make with the theoretical maximum mass that you could have made. And then we express this as a percentage. It's never going to be 100% because you're never going to make as much product as you theoretically could have done. And this is for a number of reasons. If you have a reversible reaction, then it's extremely unlikely that equilibrium is going to lie all the way over on the right-hand side. Otherwise, it kind of wouldn't be a reversible reaction. So basically, that reaction has not gone to completion. It's not finished, and therefore we haven't made as much product as we expect. The second reason is that very, very commonly the reactants that you're mixing together are going to find something else to react with, particularly oxygen. And so instead of making the product you wanted to, you're making a different product. And then the third reason, which is incredibly common, is that some of the product may be lost during extraction. If you think about the chemical reactions that you've done in a science laboratory, there's always going to be a little bit of residue left on the inside of the beaker or on the spatula you've been using, and that's still true in major industrial processes. So there's going to be a bit of product left on the reaction vessel, on the pipes that are used to pump that product somewhere, and all those things add up and they're all going to reduce the percentage yield. Solutions are made up of a soluble substance called a solute, dissolved in a liquid called a solvent. Concentration is a measure of how many particles there are in a set volume of that solution, and we can calculate it by dividing the mass of the solute by the volume of the solvent. This is actually a really easy formula to remember because the units for concentration are going to tell you what calculation you need to do. If you're asked to give concentration in grams per decimetre cubed, you're going to take the mass in grams and divide it by the volume in decimetres cubed. The easiest way to lose marks here is to forget that your mass needs to be in grams, so if it's given to you in kilograms or in milligrams, you would need to convert it, and the volume needs to be in decimetres cubed. So if you're given a volume in centimetres cubed, you need to divide it by 1,000. If you're taking the higher tier exams, you also need to be able to complete concentration calculations using moles per decimetre cubed rather than just grams per decimetre cubed. Now, it's fairly unlikely that they would give you the moles. So what's more likely is that they give you a mass and then you need to work out how many moles there are based on that mass, using mass is Mr. Mole, and then divide by volume to get the concentration in moles per decimetre cubed. Sometimes AQA like to make their titration calculations in particular a little bit harder by adding on a conversion between grams per decimetre cubed and moles per decimetre cubed right near the end. So it's worth remembering that you know how to convert between grams and moles. You're just using mass is Mr. Mole. And so the conversion between grams and moles is exactly the same as the conversion between grams per decimetre cubed and moles per decimetre cubed. They're both per decimetre cubed, so you can kind of just ignore that bit. And so you can use relative formula mass really easily to convert between these two sets of units. A very strange chapter in the AQA specification that I have never actually seen them examine is asking you to balance an equation using masses and using moles. So the idea here is that if you know the relative formula mass of every substance in the equation and you know the mass of every substance in the equation, then you can work out the number of moles, and by turning that into the simplest whole number ratio, you can balance the equation. But it's a bit of a strange method to do because usually you could just balance the equation by the traditional method. But presumably if they ever do examine it, you're going to have to use their method. So let's look at this quickly to see how we would do it. So first of all, you need to know the relative mass of each of the substances. How much would 1 mole have a mass of? So iron, we can look up on the periodic table, that would just be 56. And then 2 chlorines in a chlorine molecule would give us 71. and then a single ion with 3 chlorine would give us 162.5. So then if I divide each mass by those numbers, I find out that this would give me 4 moles of iron, it would give me 6 moles of chlorine, and it would give me 4 moles of iron chloride. And so if I simplify that ratio, instead of being 4 to 6 to 4, it can be 2 to 3 to 2. And this is exactly what I see when I look at the balanced symbol equation. In every chemical reaction, there's one reactant that's going to run out first, and we call this the limiting reactant, whereas there's another reactant that there's too much of, and this is referred to as the excess. You may be asked in a chemistry question to work out which reactant is the limiting one. Now, unfortunately, this isn't as simple as just working out how many moles there are of each one, although you are going to need to do that, and it will probably be the first 2 marks of the question. The trouble is you need to look at the symbol equation to see what ratio those reactants should be in. So if we look at this example here, in this example, we need 2 moles of magnesium for every 1 mole of oxygen. That's what the symbol equation is telling me. So if I calculated that I had 3 moles of magnesium and 2 moles of oxygen, even though there's more magnesium, the magnesium is still the limiting one because there's not enough more. There's not twice as much more. Atom economy is a theoretical calculation. In other words, it's one we can do without any real-life data. We do it based purely on the symbol equation. And what it tells us is what proportion of the reactants we put in have ended up as useful products. You can kind of almost think of it like efficiency for chemists. So what we're going to do is we're going to compare the mass of the useful product with the total mass of all products. Now, in the AQA specification, you'll see this listed as the mass of all the reactants, and that will absolutely give you the correct answer. But it's worth bearing in mind that we know, because of the law of conservation of mass, that the mass of the reactants and the mass of the product will be the same as each other. And so if you've already calculated the mass of the useful product, well, you're halfway there to calculating the mass of the total product. And so that's going to save you just 30 seconds in the exam, which I would recommend doing. So if we go back to our example with the apple pie, we could have 10 kilograms of ingredients, but only make 9 kilograms of pie, because some of what we've had has been wasted. There's been things like the apple cores and the peelings that we wouldn't want to go into our pie. So our atom economy would be 9 divided by 10 times by 100, which would be 90%. We care about atom economy and aim to have high atom economy because reactions with high atom economy are going to save resources, they're going to save energy and therefore be more sustainable, and ultimately they're going to save us money as well. When describing the method for the titration required practical, you need to be confident naming equipment such as the burette, which contains the solution that you do know the concentration of, the volumetric pipette, which is used to measure a set volume of your unknown concentration solution, and a conical flask, which is used so the solution doesn't splash when you're swirling in the way that it would if you used a beaker. The conical flask should be on a white tile, and this is going to allow you to clearly identify the colour change. You should talk about how when you're measuring volumes on the burette, you're doing this at eye level, looking at the meniscus and measuring from the bottom of the meniscus. When you write your method, it needs to make sense and actually work, so you need to mention that you're going to use an indicator so that you can identify the endpoint when you see the first permanent colour change. You need to talk about actually adding the two solutions to each other, swirling to keep the mixture homogeneous, also going dropwise when you get very near to the endpoint, and crucially recording the volume when you reach the endpoint. And then you need to repeat this practical until you have concordant data, which is data within 0.1 centimetres cubed of each other. To complete titration calculations, you firstly need to work out the moles of one of the reactants. So this is going to be the reactant that's been added from the burette, because that's the one that you knew the concentration of, and now you also know the volume that you've added. So you multiply together that concentration and the volume, which you've converted into decimetres cubed, to get a number of moles. You're then going to look at the symbol equation to work out the moles of the other reactant. Now, a lot of the time, you're just going to be given hydrochloric acid and sodium hydroxide, and they're in a 1-to-1 ratio, and therefore you don't need to do anything with the coefficients. But if you're given sulfuric acid in particular, really pay close attention to the coefficients in that symbol equation to see whether you need to double the number of moles or divide the number of moles by 2, or even something different if you're given different reactants. Finally, you're going to use that second number of moles and the other volume that you haven't used yet to work out the concentration of the missing reactant. The last thing that the triple scientists need to be aware of is that regardless of the identity of a gas, 1 mole of gas will take up 24 decimeters cubed of space if it's under standard conditions, so room temperature and room pressure. Now, this allows you to do some calculations. So for instance, if we say that we've got 12 decimeters cubed of propane, I can say, well, 12 divided by 24 is 0.5 mole. And then I could look at my simple equation here and say, well, propane and oxygen are in a 1:5 ratio. So therefore 0.5 moles of propane will react with 2.5 moles of oxygen, and that would give me a total volume of 60 decimeters cubed. But the thing is, I can actually skip some of these intermediate steps, because if I know that 1 mole of gas is going to take up a certain volume, regardless of what the gas is, then actually I don't need to know the exact number of moles. I can just take that volume and multiply it by 5, and I would get the same answer. That's it for Unit 3, and I would now strongly recommend that you go and do as many practice paper questions as you can get your hands on. Thanks very much for watching, and if you did find the video useful, don't forget to like, subscribe, comment and share for more GCSE chemistry videos coming soon.